In this video, we're going to talk about section 1.2, and we're going to focus first on patterns. So to talk about patterns, I want to first discuss some patterns we might know from our previous math classes. So the first pattern is the pattern of numbers that go from 1, 2, 3, 4, 5, 6, and you get the idea. We call this the counting numbers. But in math, the formal name is the natural numbers. The next pattern we like to look at is the pattern of numbers that includes 0. So basically, it's just like the counting numbers, except we throw the 0 in there. In that case, these are called the whole numbers. So the whole numbers includes the number 0. The third pattern of numbers are the ones that include the negatives. And then, once you get through the negatives, you start with the whole numbers. And they keep going forever. These are called integers. Integers are positive and negative whole numbers. Wow, there isn't two I's there. Positive and negative whole numbers. And there we go. Okay, now what we notice about all of these numbers is that they all increase by 1. And what that means is literally adding 1 each time. So in every single one of these, the whole numbers, the natural numbers, and the integers, here I'll go on the top just because of space, you are always adding 1 to get to the next number. Let's look at this set of numbers. So this set of numbers, 2, 4, 6, 8, 10, most of us recognize this to be even numbers. Unlike the natural numbers, the whole numbers, and the integers, these numbers are adding 2 each time. Now that's not the only thing that makes even numbers special. But for the moment, I want to talk about the other set that we usually associate with the even numbers, and that's the odd numbers. The odd numbers also, just like the even numbers, if you look at how the numbers are increasing, they're also increasing by 2, which is a little bit weird because most of us associate 2 to the even numbers. And the reason we associate 2 to the even numbers is that all the even numbers are divisible by 2. But that's not the case with the odd numbers. The even numbers are divisible by 2. Odd numbers are not. However, we notice they have a common pattern. You add 2 to get to the next number in the pattern here, okay? The difference is the starting place. The even numbers are starting with the number 2, whereas the odd numbers are starting with the number 1. And that's why we're getting these kind of opposites numbers, even though they're both adding the same number every time. Okay, so this pattern of numbers does have a name, and I'm going to use DEF to represent definition. So I'm going to give you a definition. A sequence of numbers, which is what we're looking at, have a specific order and often a common pattern. Now, the reason it says the word often means that it's possible to have a sequence of numbers that we can see the order, but really can't see the pattern. We won't really deal with that too much. That's kind of really high level math and science. But we kind of I wanted to mention that because it is important to understand that not everything is always going to work out lovely. The things that work out lovely are actually really great. Okay, I want to show you a famous example of a sequence. This is called the Fibonacci sequence. Oops. Fibonacci. So Fibonacci is a mathematician, an Italian mathematician, who discovered a sequence of numbers that actually ended up being a lot more important than most people realize. Okay, so to share the sequence, I'm going to kind of share the story that started the sequence. And it uses rabbits, okay? And it uses the idea that Fibonacci started with one pair of rabbits. Okay, so this is my attempt at writing a pair of rabbits. Wow, those are supposed to be rabbit ears. They look like sad little detached M's. Okay, hold on, let me try it again. Boop. All right, there they go, rabbit ears. All right. And what happens is every pair of rabbits grows up, okay? And in a month, they're able to procreate together and create new rabbits, okay? So in month 1, we have 2 baby rabbits. But in month 2, those baby rabbits get much bigger. And by month 3, they are able to produce another set of baby rabbits. Okay, now I'm fully aware that we're kind of ignoring the fact that they're siblings. And we're kind of ignoring the fact that we're assuming that every little pair of bunny rabbits that comes out is a boy and a girl. Okay. But for the moment, just suspending that understanding, we're going to follow this pattern. Okay. So in month 4, here's what happens. The first set of rabbits are still around. Oops. Trying to kind of put them together. The first set of rabbits, they're an adult, they're still around, and they can have another set of babies now. Okay. Before I write their set of babies, the baby rabbits from month 3 are going to mature into adult rabbits themselves. All right. Now, the original rabbits, here, I'll give them the yellow color. There's the original. They grew up from these little babies over here. These original rabbits are going to now have another baby. So this is month 4. Okay, last month I'm going to draw out here. So in month 5, here's what happens. The original rabbits are still able to produce babies. Okay. So they're going to have some babies. The pair of rabbits that just grew up in month 4 are going to have some babies too, but they're also still around. So here, let me just draw them. That's this set. Poop. Okay. But they're going to have some babies also. And then these babies right here, they're going to grow up in this month. So next month they can have babies. Okay. But the original rabbits, they have a set of babies. And the rabbits that just came from month 4, they had a little set of babies too. Okay. So here we go. I want to count up, and let me kind of zoom out a little bit here. I want to count up how many rabbit pairs we have. So in month 1, we had 1 pair of baby rabbits. And then in month 2, that same pair of baby rabbits grew up. And then by month 3, they were able to finally have some babies themselves. So we have 2 pairs of rabbits in month 3. So month 1, we have 1. Month 2, we have 1 pair. Month 3, we have 2. Month 4, we have 3 pairs. And then by month 5, month 5, we have 5 pairs. Okay. Now I could keep going, but I want to look at the pattern that we're seeing here. Okay. Here's what happens. We start with our first pair of rabbits, letting them grow up. And then we finally get a new pair of rabbits coming in. That came from the first pair of rabbits. So here's what I want to notice, that if I added 1 and 1 together, I get 2. And if I add 1 and 2 together, what do I get? 3. If I add 2 and 3 together, that gives me 5. And what I'm hoping you'll see is that is the pattern of numbers that we just had up here in the pairs of rabbits. Give me a second to erase all that. And I'm going to write down what I just said. So I started with 1, 1, 2, 3, 5, and I'm writing that down, 1, 1, 2, 3, 5. And what I'm noticing is if I add 1 plus 1, I get 2. And if I add, so that's starting with the first 2. And then if I add the second and third numbers, that would be 1 and 2, I get 3. Sorry, that kind of looks like a 2. Let me make it look more like a 1. There we go. And then if I add these two together, 2 and 3, I get 5. So now the question is, if we add these two together, what do we get? 3 and 5, that gives us 8. And then 5 and 8 gives us 13. 8 and 13 gives us 21, and so forth. So the pattern is we add the two previous, sorry, that's not how you spell previous, 2 previous numbers in the sequence to get the next number. That is the pattern of the Fibonacci sequence. And I know what you're thinking. Big whoop, right? Like, so what? Who cares? That's not a big deal. I mean, yeah, it's kind of cool. Like you're adding the numbers, previous 2 numbers every time to get to the next number. But how is that all that exciting? Well, turns out the Fibonacci sequence actually has a lot of applications in our world. And you have seen applications of the Fibonacci sequence probably without even realizing it. Okay, let me show you 2 of the most famous applications of the Fibonacci sequence. So first, I'm going to draw these numbers in this sequence as boxes. Okay. In other words, I'm gonna kind of look at it as the sides of the box are that length. So I'm gonna draw, and let me kind of zoom out just a smidge because I want to give myself enough space. Okay, so I want to draw 2 boxes. This is my starting boxes, and each box is a unit of 1. Actually, here, let me draw a 1 so I can enclose it in the box. So this box is unit 1 on both sides. Pick your unit, 1 inch, 1 centimeter, I don't care. But every side of that box is 1 centimeter or 1 inch. Okay, so using the sides of these 2 boxes, that forms right here, these 2 sides form 2 centimeters. So I'm going to build a 2 centimeter box right off the sides of them. Okay, and that's all 2 centimeters on each side. Okay, and then using the sides down here of these 2 boxes, those are going to be 3 centimeters. Oops, a little bit bigger. Trying my best to make them look like squares. 3 centimeters. Each side of that box is 3 centimeters. Okay. And now I'm going to keep building off of the sides here. So this is now 5 centimeters. 5 happens, of course, to be the next number in the Fibonacci sequence. And then above here, we would have, oops, 8 centimeters. I'm kind of running out of room. All right, cool. And you get the idea. You can keep going. Here's what's cool. If you take the corners, the opposite corners of each box, and kind of build the opposite corners of each box, and starting from the center first box. So technically, I'm going to start from this box right here. And I'm going to connect this corner to this corner, 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 and so forth. I just keep going opposite corners on each box. It forms a spiral. Oops. This spiral is special Actually, if you just look at that green spiral, you have seen this spiral in nature. You see it on beach shells. You see it in flowers. This spiral exists all over the place. This spiral that is based on the Fibonacci sequence actually is out in the real world. And there is a completely reasonable explanation for why that is. We're not going to talk about it. What I am going to show you is another example of the Fibonacci sequence in the real world. If you were to divide the numbers of the Fibonacci sequence, so I'm going to start with 5 divided by 3. So I'm looking at the third and fourth numbers of the Fibonacci sequence, okay? 5 divided by 3. You will end up getting 1.6666 repeating, okay? That goes on forever. If you were then to go to the next two numbers, which would be 5 and 8, maybe I should write the Fibonacci sequence down again. 1, 1, 3, 5, 8, 13, and 21, and then it keeps going. Okay, so if we were to divide these two by each other, 3 and 5, and now I'm going to divide 5 and 8, and that gives me 1.6. And then I divide 8 and 13. I'm sorry, yeah, 8 and 13. So first it'll be 13 and then 8. And that gives me 1.625. And then I'm going to divide 21 and 13. And you're like, okay, is there supposed to be a pattern forming? Yes, there is. There is a pattern forming. It takes a while to form. What I want you to notice, though, is that it's kind of staying around 1.6. Okay. And actually, if you keep going and you keep dividing, it ends up, these numbers keep getting closer and closer to 1.61. That number, 1.61, is called the golden ratio. It even gets a special label like pi. Here, let me give it the approximate symbol. And that is phi. Okay. And this represents the golden ratio. And the golden ratio is also everywhere. The golden ratio is used all over the world. We use the golden ratio in our own art. The golden ratio is found in the Mona Lisa. It is incredible. So the Fibonacci sequence actually ends up being all over the world and kind of has this crazy effect on our art even, and how we build buildings. It's just crazy, and it's in nature. It's kind of cool. Okay, so let's go ahead and come back from these kind of fun examples, and I want to go ahead and zoom back in a bit. I know this kind of got big, but I want to look at another definition. A little bit easier this time. This definition is an arithmetic sequence. Arithmetic sequence. An arithmetic sequence is a sequence of numbers produced by adding or subtracting by a constant. We actually have a name for that constant. That constant is called the common difference. And we often use D to represent the common difference. Okay, we've actually seen some examples of arithmetic sequences. Actually, that's what I started with when I started talking about patterns. So, for example, whole numbers. Those were the ones that went from 0, 1, 2, 3, and it kept going forever, dot, dot, dot. Okay. Whole numbers are an example of arithmetic sequence because in this case, the difference or the common difference between each number is 1 because I add 1 every single time. Another example we talked about were even numbers, also odd numbers, but we'll just select even numbers. Sorry, I started to write odd because I literally said it. even numbers, 2, 4, 6, 8, and so forth, dot, dot, dot. In that case, the common difference is 2. So exciting. Well, let's look at some other examples. Let's look at 1, 4, 7, 10, 13, dot, dot, dot. So this is an arithmetic sequence because the difference between each number is 3. It's adding 3 every single time. So I know the difference is 3. And I can produce more terms of the sequence, which they often ask you to do when they ask you to identify the sequence, whether or not it might be arithmetic, or another one we're going to talk about. So the next 2 terms of the sequence, or I could do as many as I want because I didn't specify, would be 16 and then 19. And why not throw a third one in there for the heck of it? So 22. So adding 3 each time will get me the next number in the sequence. Okay, let's try another one. Let's see. 17, 10, 3, -4, -11, -18, dot, dot, dot. Okay, so this time we're actually not adding a positive number. We could think of this as adding a negative or subtracting a number every time, which we are allowed to do. That was under the definition of arithmetic sequence. So each time we are subtracting 7. So in this case, the common difference is -7. And the next terms in the sequence we can find by continuing to subtract 7. So starting with -18, if I subtract 7 again, I would get -25. If I subtract 7 again, I would get -32. And here I'll do one more time, -39. Since I did 3 last time, I'll do 3 this time. Why not? Awesome. And there we go. Those are arithmetic sequences. Now I mentioned there's another kind of sequence we're going to look at. And let me go ahead and define it. That is a geometric sequence. A geometric sequence is a sequence of numbers produced by multiplying or dividing by a constant. And we call that constant the common ratio, which we use R to represent what we are multiplying by or dividing by. Now, I want to make a note here because I think it's important. Note, if you talk about dividing a number by 2, like let's say I divide 4 by 2, okay? Another way of thinking of that is multiplying 4 by 1/2, okay? They both end up giving me 2. And you might remember, and we'll review this when we get to fractions, that when you divide by a number, you can rewrite it as the multiplication of the reciprocal. That was kind of like a fraction concept. But what we're doing is we're basically, a way of thinking of this is thinking of it as taking 4 and putting 2 in the denominator, which is a division and gives us 2. Okay. So we could think of it like that. Again, it's kind of coming off of the whole fraction idea, but I'm making a mention of that because sometimes the common ratio might be a fraction. And if it is, that's because we were talking about a division. Okay, let's look at some examples, shall we? Let's do. Okay, 2, 4, 8, 16, 32. All right. And hopefully we see the pattern pretty regularly or readily for multiplying. It is multiplying, and it looks like we're multiplying by 2 every time. So that would be the common ratio is 2. And if I wanted to produce the next 2 terms, or let's do next 3 terms, sorry. The next one would be 64 and then 128. And here, I'm actually going to grab my calculator. I don't remember the next one off the top of my head. Oh, 256. And you may want to grab your calculator too if you need it. Maybe you already have it. That makes you awesome. Okay, let's try another example. Here, let's get some bigger numbers going. Since we got our calculator. 324, 108, 36, 12, 4, ... Okay, so on this one, I'm going to find the common ratio by dividing. Okay, and basically what I'm going to do is I'm going to divide 324 by 108 and see what I get. Putting that in my calculator. All right, when I divided that, I got 3. So the idea is to go from here to here. I'm thinking they divided by 3. So I'm going to try that, make sure I get 3. I'm sorry, when I divide 108 by 3, that I get 36, and I do, and there it is. The common pattern is they're dividing by 3 every time. So in this case, the ratio is 1/3. Remember, because I said we're going to write it as a fraction when we're dividing. Okay, so to get to the next term, I'm going to divide 4 by 3. That's not as exciting as it sounds because I'm not going to simplify it since 4 divided by 3 doesn't come out to a very nice number. And if I divide that by 3 again, it actually gives me 4/9. And here's why. Because I'm taking 4/3, timesing it by 1/3, and that gives me 4/9. I don't want you to get too hung up on that. We will talk more about fractions later, but basically what's happening is once we get to the fractions, we're basically putting 3 or timesing 3 into the denominator every time. And that's dividing by 3 every single time. Okay, so it's the denominator is increasing by 3 as we go through this. All right, nifty. Now, sometimes there isn't a name for the sequence, but there might be a pattern that we could find and possibly produce. So it may not be arithmetic, it may not be geometric, but maybe we can find a pattern. One of those ways of finding patterns is something called finite differences. Finite differences is when we subtract repeatedly until a pattern emerges. So we're going to subtract repeatedly until, wow, that's a weird U, until a pattern emerges. All right, let's look at an example. Let's say we have 10, 21, 35, 52, 72, ... Okay, and we're like, all right. So readily, it doesn't look like there's a pattern because when I look at the first two, it's 11. It has a difference of 11. And then the second two, it looks like it's a difference of 14. Okay, but here's what we're going to do. I'm going to actually take a second. I'm going to rewrite this thing. I'm going to go ahead and rewrite 10, 21, 35, putting a little space, 52, and 72. And here's what I'm going to do. I'm going to repeatedly subtract. So when I look at the difference between these two, it's a difference of 11. When I look at the difference between these two, it's a difference of 14. Okay, difference between 35 and 52. I'm going to use my calculator. I came up with 17. Difference between 52 and 72 is 20. And now I'm going to look at the difference between the differences. So looking at the difference between these two. So the difference between 11 and 14 is 3. And 14 and 17 is also 3, and 3 again. Aha, so there we go. That means I could find the next numbers in this sequence kind of using this idea here. So let's do it. If I did another 3, I'm going to build it up basically to kind of get to the next number. That would give me 23. And then to get to the next number, that means I'm going to do 72 plus 23, which is 95. So that would be the next number in the sequence. Here, I'm going to write it down and let's just do it one more time. So adding 3, that gives me 26. 95 plus 26 adds up to 121. And that is the next number in the sequence. Cool. Okay, so let's try it one more time. This time, maybe give it a shot yourself. Pause the video. See if you can do it. Okay. 2, 9, 22, 41, 66, 97, ... Okay, so use the differences, the finite differences to see if we finally get a pattern to emerge, and then find the next 2 numbers in this sequence. Okay. And I'll go ahead and work that through. So let me write them out a little bit spaced. 2, 9, 22, 41, 66, 97. Okay, so first 2 numbers. I want to go ahead and subtract 2 and 9, and that gives me 7. 22 minus 9, I believe that's 13. I'm a little tired, so I'm just going to double check. Yep, it's 13. Okay. 22 and 41. Let's see, I'm getting 19 on this one. 41 and 66. I'm getting 25. And then 66 and 97. I get 31. All right, I'm going to do this again. So 7 and 13, that is 6. 13. Oh, sweet. Okay, cool. It worked. All right, I don't have to keep going. You could just keep going. You keep going until you find a number that's repeating. But here we go. We found it, and we're able to build back up to get to the next one. So let's see, 37, which I'm going to add to the 97. And I get 134 when I add those together. So there's my next term. Do one more. Adding another 6, which gives me 43. And then 43 plus 134, I get 177. And there it is. The next 2 numbers in the sequence. And there you go. There is patterns.